In this video, we'll deal with the real vector spaces. Before that, let us look at the forms of a vectors can be presented. Before the 18th centuries, vectors can only be presented geometrically, which means that for whatever vectors that you're dealing with, you only can draw it on either a two-dimensional space diagram or a three-dimensional space diagram. This limits the progress of science and mathematics because there is no ways for us to draw a fourth, fifth, and even higher dimensions on a three-dimensional space. But thanks to the contribution of few mathematicians in the 18th centuries, they found out that vectors can also be presented analytically, which means that you can write down the vectors in this form within the bracket. And with the possible presentation of vectors in the analytical form, it paved the ways for higher dimension and more advanced calculation and formulation. Today, the quantum physics deals with 10 and even 11 dimensions. So can you visualize it? It is impossible for us to visualize it or sketch it on a three-dimensional space diagram. But in the analytical form, you can write it as many as you want. You can write 1, 2, 3, 4. So this is a fifth dimensional order for the vector space. Now let us look at what is a vector space. A vector space is a set that is closed under finite vector addition and scalar multiplication. In layman terms, a vector space is a collection of objects called vectors, which may be added together or multiplied by numbers called scalars. So this collection of objects, they must fulfill the conditions, which is the added together and multiplied by numbers, before this collection of objects can be called a vector space. So let's look at this diagram. Within the blue line boundary, the members here, the objects here are real number. So we want to know whether this set of real number is a vector space or not. So we have to check with the two conditions here: added together, vector addition, and scalar multiplication. First, you just randomly take any two members from the group of real number here, and you sum it up, and you'll find out that the new products or new members here, they are real number, which means that they are still belongs to this family of objects, the real number objects. Let's look at scalar multiplication. You randomly multiply any of the members here with a scalar, a constant, be it a 5, 0.5 or negative value, you'll still get a real number here. So this new real number is still within the family of real number. And since that vector addition and scalar multiplication are being fulfilled by all the members here, we say that this collection of objects is a vector space of real number. So to visualize what is a vector space in our real world, so just think about it. A vector space of real number can be presented as a cookbook for spaghetti. And the set of objects here are the ingredients. The vector addition and scalar multiplication are the instruction to prepare the recipe and cook the food. So as long as the members of the objects, the collection of the objects fulfill the vector addition and scalar multiplications, then we say that this collection of objects, they are a vector space of a real number. The vector space does not stop at real number. It could be a real number for two-dimensional space, three-dimensional space, where the members here, U1, U2, U3, they are all the U are within the realm of real number. And vector space could be expanded out of real number. It could be a vector space of a polynomial equations where the members, those polynomial equations within this boundary, belongs to the polynomial equations vector space. Similarly for matrix, you can have a 2 by 2 matrix, any real number here. So this group of matrices that form a vector space of 2 by 2 matrix. And you even can have a vector space of odd number, even number, and so on. So let's represent it with a simpler example. Let's say I want to have a vector space of concrete. So the members of this concrete can be a red concrete, gray concrete with a different grade, 33, 43, and 53, with a different strength and compressive strength. So the concrete vector space where the objects are the different types of concretes, and addition means that you can mix the concrete together, and multiplications means that you can get a different weight of the concrete. So if the members here fulfill the addition and multiplications conditions, we say that this group of concretes they form a concrete vector space. So previously we know that in order for a collection of objects to be known as a vector space, to form a vector space, there are two conditions must be met, which is the vector addition and scalar multiplication. But these are just the two fundamental criteria. There are actually 10 vector space axioms that you need to prove in order to check whether the collection or the group of objects can be called as a vector space or not. So the first one will be the most straightforward, which is the addition. Just imagine you randomly pick two members from the collection of objects and then you sum them together. The new product must be still within the realm. In the previous case, in the previous example, is the real number. So 1 is a real number, 3 is a real number, so 1 plus 3 equals to 4. So 4 is still a real number, which is still within the boundary here. The second axiom is that the addition of two members or two objects here must be the same, even though you reverse the sequence. So 1 plus 3 equals to 3 plus 1. And the third one is the similar one, 1 plus 2 plus 3. So you can compute the calculation or the operation within the bracket, or even you can adjust it u plus v, so 1 plus 3 plus 4. So you should get the equivalent answer for the left hand side and the right hand side. And the fourth axiom is the spatial one. There's an object 0 here, so the 0 here is the 0 vector, and a 0 vector does not necessarily equal to a vector full of 0. So depends on the condition given. So this 0 vector, when you add it to any of the members of that group of objects, you must get back the original objects. So in some cases, the 0 vector here is the 0, or a vector full of 0, but in certain special conditions, the 0 vector does not necessarily has to be a 0. And the fifth axiom is a special one as well, because there is an object, the inverse, the negative of the object, which is still within the group of objects. When you sum them together, you should get the 0 vector here. Similarly, this 0 vector must be the 0 vector similar with the fourth axiom here. The sixth is about scalar multiplication. When you multiply a scalar with the members, any members in the group collection of objects, that new members should still within the collection of objects. And these 7th, 8th, 9th are similar with the scalar multiplications. It's just that the sequence is being adjusted. So the last one, the 10th axiom, is that there is a vectors, or where there is a vectors when you multiply it with the member of any of the member from the collection of the objects, you will get back the original object. So these 10 axioms, you have to carry out the proving all the 10 axioms to show that whether the collection of objects there belongs to a vector space or not. But pay attention to the axiom number 4, 5, and number 10. They are a bit spatial, which requires your attention. I'll show you an example later on. So let's look at a simple example here. The first example. Imagine that you have a set of objects x and y. This is a vector, the member of the vectors, where the x must be equal or larger than 0 and y larger or equal to 0. So let's take a random members from this set of objects as long as they fulfill the criteria here. So let's try out with the first axiom, which is the addition. So I can assume that the x and y to be 1, 1, because x is larger or equal to 0, y is larger or equals to 0. They are in the first quadrant realm. So any members here, any vectors on this boundary is considered valid. So I'm just going to randomly pick a member here, 1, 1, and another one is 20 and 1. So I end up with the 21 and 2. So these 21 and 2, they are still within the region here. So I say that the first axiom is fulfilled. Next, I try with the sixth axiom. Normally we try with the first and the sixth because these two are the fundamental one. Once we prove that the first and sixth are fulfilled, then we move on with the fourth, the fifth, and the 10th. So let's look at the sixth one. I can assume that k to be 4 because k can be any scalar. So it could be positive or negative. In this case, we try with the positive first. So 4 multiplied with the one of the member here, I still get the 4 which is still within the region here. So I say that, okay, for the positive scalar, this sixth axiom is fulfilled. But let's check on with the negative one because k can be positive or negative. So when I have a k with a negative value, it seems like I end up with -5 and -5, which is in this region out of the boundary here. So I say that the sixth axiom was not fulfilled because the scalar multiplication will give you a members which is out of the boundary here. And we say that this group of vectors, they are not a vector space. Let's look at example number 2. So now we have another vectors, a group of objects xy where the multiplication of xy would give you 0 or larger than 0. So based on the sketching here, I know that the region for this condition to be fulfilled will be the first quadrant and the third quadrant, because for the x and y value, if both are positive, you'll get larger or equal to 0. If both are negative, you'll get positive or larger than 0 too. So now let's try with the sixth axiom first. I can assume that the scalar can be a positive or a negative value, and I can randomly pick any member, one member from the first quadrant and one member from the third quadrant, 1, 1, -4, -5. So when I multiply with the positive scalar, I get the new members which are still within these two regions. When I multiply it with a negative value, so let's use the 1, 1 here as the u, I still get -2, -2, which is within the region here. And if the case for the member with -4 and -5, I get 8 and 10, which is in the first quadrant. So it seems like the scalar multiplication will give you a new members which is still within the region here. And I said that the sixth axiom is being fulfilled. But let's look at the first axiom, the addition. Let's imagine that I have one member here, a random member taken from the first quadrant and a random member from the second quadrant. When I sum them together, well, I get the new members which is still within the third quadrant, which is still within the region. But we have to try more proving because this is not conclusive yet. Let's try with another set of factors here. So let's imagine that u3 taken from the third quadrant is -4 and -1, and u4 is the member from the first quadrant, 2 and 6. When I sum them together, it seems like I obtain a vectors which is outside of this region, where I get -2 and 5. So it should be in this region, the second quadrant. So it seems like the addition of the members, any random members here, does not guarantee that you'll get back the new vectors which is still within these two quadrants, as proven in this addition here. So I said that the first axiom was violated because the addition of any members here would not guarantee you with the new member which is still within the region here, as shown in this case. If I'm going to represent it in the geometrical way, so imagine this is the first, imagine either one. So this is the first vector and this is the second vectors. When you add them together, you'll get the third vectors which is outside of these two regions. So I said that this set of members or this set of vectors do not form a vector space. Now let's look at the vector space of a polynomial equations. So this is the third order polynomial equations, which means that the highest power of the x is raised to the power of 3. And let's look at the members here. So the first member is q1, where q1 is represented by 1 plus 2x and q2 is -x squared plus x cubed. So we want to know whether these two polynomial equations they form a polynomial vector space of third order. So let's check with the first axiom is the addition. So q1 plus q2 will give you 1 plus 2x minus x squared plus x cubed. So this is within the region of third order polynomial equations because the highest power is 3. Let's try with the sixth axiom, which is the multiplication with a scalar. So I can multiply any scalar, be it positive or negative scalars with any of the members here, and I still end up with the polynomial equations which is still within the third order polynomial equations here. So most probably these two polynomial equations that form a vector space of a third order polynomial, because I haven't tried with the second until fifth and 7 until 10, but I will I'll let you try it on your own to prove that these two members of the polynomial equations that fulfill all the 10 axioms. Now remember just now when I told you to pay attention to the fourth and the fifth as well as the 10 axioms, because in some cases the addition and the vector addition and scalar multiplication will be different from our real world addition and multiplications. Let's just imagine that in another space, the addition of the members will give you the final product, which is actually a multiplications, and the scalar multiplication of a vector or a member with a scalar will give you a raised to the power of that particular scalar. So in this case, any operations that involve addition and any operations that involve multiplication, you should use the rules given here. Which means that the addition will become multiplication and multiplication becomes the raised to the power of k. And let's check whether this group of member where r is all the real numbers. So you have a set of numbers where they are all real numbers. We want to know whether this collection of objects, the real numbers, could be a vector space or not. Now I left the rest for you to try. Here I'm just going to show you the fourth, the fifth, and the seventh axioms. So for the fourth axiom shows that any additions of the zero vector where you get back the original number here. So in this case, the additions operation is actually a multiplication. So you have to multiply them together, which means that the zero vector multiply with u, which will give you back the u here. So you see, in order to get back the u, the zero vector here must be 1. So your zero vector will be 1. So such that 1 plus u will be 1 multiplied with u. So you get the u original member back. So the zero vector here shows that it is not necessarily equals to 0. It can be any other number. In this case, the zero vector is 1. Now let's try with the fifth axiom. The addition of a u with its negative component will give you the zero vector. In this case, the zero vector would be taken from the fourth axiom, which is 1. And let's look at this. The inverse of u is actually a multiplication of -1 and u. So this involves the multiplication operation, and since the rule is given, any multiplication will become raised to the power. So negative u will be u raised to the power of -1, which is equivalent to 1 over u. So you have u plus 1 over u here. And since this involves addition is multiplication here. So you have to multiply them together and you get back 1, which is exactly the zero vector that you obtain from the fourth axiom. So we can say that the fourth axiom and the fifth axioms are being fulfilled. And let's look at the seventh. So the seventh axiom is actually a multiplication of a scalar on the addition of two members here. So we know that the u plus v, because the rules is given, u plus v must be multiplication. So we have uv here. So k multiply with the uv. And since this is a scalar multiplication, you'll use the multiplication rules here and raise to the power of k. and you can split them out uk multiplied with vk. So this is actually a multiplications of two components. You can simplify them with the representative vectors here. Let's imagine that u raised to the power of k is equivalent to u1 and vk is the v1. So you can see that u1 multiplied with v1, u1 multiplied with v1, you can bracket back to the addition here. So you have the u1 plus v1, and you write it back to its original form, uk plus vk. So uk is the raised to the power, so uk here, you reverse it back to its original form, which is the multiplication. So ku plus kv, which is equivalent to the term on the right hand side, and we prove that the 7th axiom is being fulfilled. So I left it for you to try with the first, second, third, 6, 8, 9, and 10, and all the axioms here to show that this set of real numbers given by the vector addition and scalar multiplication conditions form a vector space.